This problem is what we call a calorimetry problem. Calorimetry is a fancy word for heat exchange. And what we need to do whenever we try to solve such a problem is we need to identify first off what's gaining heat and what's losing heat. So in looking at this problem, we're told that a 2 kilogram piece of copper at an initial temperature of 90.4 degrees Celsius is dropped into 3/10 kilograms of water containing an equal mass in alumina calorimeter. The water and calorimeter are initially at 15.3 degrees Celsius. What is the final of the temperature of the system when it reaches equilibrium? And again, we're told the specific heat of copper, aluminum, and water are 387 joules per kilogram degree Celsius, 899 joules per kilogram degree Celsius, and 4,186 joules per kilogram degree Celsius, respectively. Now, to give us some sort of context, the calorimeter is basically just a fancy thermometer, fancy thermos. Okay, so we're told, it's so much water is poured in. A piece of copper is placed into a calorimeter containing, water, and it's an aluminum calorimeter or aluminum cup. So the aluminum and the water, because they are in thermal contact with each other, they have the same initial temperatures. If we look at what I've done here, since this is heat exchange and Q stands for heat, we're going to have basically, well, an equation with two sides, something gaining heat and something losing heat. The law of conservation of energy says, energy can't be created or destroyed, it's just swap between the forms, if you will. So for a closed system, meaning one that's not exposed to the outside environment, one that is self-contained, if I have three objects in question and one is at a higher temperature than the other two, which happen to also then be in thermal contact with one another, when I take that higher temperature object and place it into the lower temperature other two objects, that hotter thing is going to cool off. The colder things, the things at the lower temperature, are going to then gain heat, and everything will reach an equilibrium temperature. It's kind of like equivalent to putting an ice cube in water that sits in a cup. The water and cup that the water that contains the water, presumably if they are sitting out long enough, are at the same temperature, and then you introduce a ice cube into the system, and depending upon the temperature of these different things, the ice cube will melt, the water will cool down, they will reach thermal equilibrium at some point. That example sort of ignores the fact that that's not a closed system. But getting back more specifically to the point here, so I can rearrange this equation that I have written at present to look like any gained heat equals the negative of any heat loss. So by adding the heat that I lost to the other side of the equation, I end up with this. This is a more useful form of the heat equations for us, only because they will permit us to, well, you'll see here in a second. So in going through the problem, I've indicated those variables, just taking them out. So the thing that's losing heat would clearly be the copper. The things then that are gaining heat, this would be representative of your aluminum, this is representative of water. Point to note, I was not able to put degree signs in here. There should be a degree beside the Celsius. Anywhere you see a Celsius, there's a degree. Let's go ahead and solve this problem, or maybe better yet, let's set up this problem. I will use my editing box here to maybe do a better job of laying this out. So the thing that's losing heat, so what I do is I try to write all my terms out for the side gaining heat and side losing heat. So TF minus TI plus mass times specific heat both sides of the equations look the same in the sense that each quantity has the same physical characteristics that we're concerning ourselves with: mass, specific heat, and temperature change. Where things then sort of become a little bit more of a challenge for us is the long algebra problem that's going to quickly unfold here. So I'll just go ahead and type in these values. So this thing right here, maybe I'll write above this so we can see it. This first quantity I have, MCTF minus TI, that's going to represent we'll call it the aluminum, because it's one of the objects that's gaining heat. The other one's going to be the water. The other things then that, well, the other object then on the other side would be the lonely copper that is placed into the aluminum calorimeter cup. Okay, so now if we continue to resolve this problem, as it would be, it's quickly, you're going to see how quickly this turns into an ugly mess. But it's not so much difficult because it's difficult because there's a lot of things you got to keep track of. And I will eliminate spaces where necessary to sort of keep this all together. If there's any mistakes that are, I guess, the most likely to be made, it's with the minus sign over here on the side where the object is losing the heat. Most of your problems will just be algebra, as much as I hate to say that. And I guess I can presumably type more legibly than I can write, so just bear with me here. So now we're on the other side of the equation again. Don't forget that minus sign I bolded, even though it doesn't show too much. And if you're going to screw anything else up, it might just be the thing with your variables, making sure they're all in order. And that's why I sort of strategically laid out these columns above, so I know exactly what it is I'm looking at when I'm trying to solve this problem. Okay, so that would be the next line of information that is needed. To maybe further reduce this down, I can begin to multiply these coefficients out front together, and then I'll be left with these quantities yet left in the parentheses. So writing in those terms, if I simplify this, take 0.3 times 899, I end up with 269.7 times this quantity, which we will then later distribute. By taking 0.3 times 4,186, I end up with 1,255.8, and of course still having that same quantity in the middle, equals, again, watch your minus sign. If you're going to screw anything up, you're going to forget the minus sign. 0.2 times 387 yields negative 77.4 times x minus 90.4. Another point that people sometimes will make a mistake on when they're doing this is you get these values swapped around. For every one of these, it's final minus initial, final minus initial, final minus initial. Your final temperature is going to be less than your initial temperature for the copper. Okay, that's why it's so large, but the pattern still remains the same. Our next step then will be to distribute these values out front through each term inside the parenthesis. So now if I go to multiply the 269.7 times the x, I'm going to get the same thing, 269.7 x. It's just the x. But now I still have to distribute that minus 269.7 through to the minus 15.3. When I multiply those values, I end up with minus 4126.41. Okay? Again, mistake to be made if there is one. You're going to forget about the minus sign here. And then adding that on to the next term, we take the 1,255.8, multiply that by x, we still get the same thing. Minus sign, because it's still there, 1255.8 times 15.3 yields 19,213.74. Now all equals negative 77.4x, because it's negative. Now, commonplace for another mistake. Don't forget your minus sign here, your minus sign here. A negative times a negative is a positive. So our end result for that quantity will give us 6,996.96. And this then reduces, so this is our reduction of our next set of terms. What we're going to do now is go through, and I'll highlight this so you can see. You see we have x there, x there, x there. We're going to combine our like terms. I double underline those because they are the numbers without any variable. That's what we're going to do next. So our next line, if I'm going to first simplify and then I will move things across. So in resuming with this process, If I combine the x's on the left-hand side of my equation, I end up with 1,525.5 x approximately minus 23,340.15. That's just a number with no variable, and then I haven't done anything with these terms on the other side, so they still are what they are. Now I am going to add, let me write this, I'll write this here so we can see it. I'm going to add 77.4x to both sides to get a positive value out of this, and to eliminate that value off of the other side, so that's 0. When I add these two together, what it does is it reduces our left-hand side of the equation to give us 1,602.9x, and then I'll just go ahead and continue to write this out for the sake of doing it, and then we're left with this value here. Now our job is to add the 23,340.15 to the other side. Get that there. Okay, when we do so, that term goes away, leaving us, I'm going to jump to the top up here to give us the room we need. When you add those values together, you get 330,337.11. And the last step then for us to entertain is to divide, here's my long division sign, divide both sides by the number that's multiplied by our variable, which is 1,602.9, and we'll do the same. And in solving for x, when we divide our numerator by our denominator on the right-hand side, we should end up with, what do we got here? 18.92 and degrees Celsius. Okay, so again, there should be a little degree symbol there. So if I can maybe just sort of recap here very quickly, a little degree. If I can recap the trouble points you're going to encounter in trying to solve one of these problems. It's long. Is it difficult? Not necessarily if you can keep track of your numbers. It's the algebra. Don't forget your minus signs, especially this one out front over here for the copper, in this case that's losing the heat. It's going to be distributed through eventually. As we see, it gets combined, well, it gets distributed through the entire point, and if there's a mistake to be made, it's going to be forgetting that, because combining that with that gives you a positive number, which we see manifest itself there. Another point where you're going to screw something up if there's a mistake to be made, it's just with your signs. Pay attention to your signs. If you can keep track of your signs and you start everything off by laying out this table very nicely as I've done here, the problems you encounter with calorimetry and heat exchange are relatively diminished.